In this problem we have a boat with a spotlight on it. Now we're told the spotlight on this boat is 2.5 meters above the surface of the water. So we'll call this 2.5 meters. And we're also told that the light strikes the water 8 meters away. So the light comes down here, hits it 8 meters away. So this distance here is 8 meters. Okay? It strikes the water, and because this is a different index of refraction, it goes off at a different angle. So we have our incident angle and our transmitted angle. So those two are going to be different. Now, we're also told that the depth of the water is 4 meters. We want to find what the distance is here to where it touches the ground. So how far away does that light hit the bottom of the water, or the bottom of the ground underneath the water? Okay, so we're going to have to use Snell's law. N initial sine theta initial equals N final sine theta final. Okay, initial index of refraction is 1 because that's in air. Final index of refraction is the index of refraction of water, which is 1.333. Okay, now we just need to figure out what our angles are. This is basically a trig problem with a little bit of physics. We just need to figure out what our angles are. Okay, so theta initial is going to be what? Well, this is actually pretty much a known. We just have to do a couple of calculations. We have to figure out this angle here. Okay, once we figure this angle here, we'll be able to know what theta initial is because it's just 90 minus that angle. We know these two lengths of this triangle here. Okay? So we'll be able to figure out what that theta initial is just by using these two. So if we use tan, we're going to call this alpha. So if I say tan alpha is going to be equal to opposite 2.5 over adjacent 8.0. 0.5 meters over 8.0 meters. Okay? So I take the tan inverse. Alpha is 17.35 degrees. Okay? Now initial angle is going to be, well, plus alpha equals 90 degrees, right? So this whole thing is a 90-degree triangle, 90 degree. And so theta initial is just going to be equal to 90 degrees minus that 17.3 degrees. So theta initial is just now 72.65 degrees. Okay? Now we can't do the same with the transmitted theta because we don't know any of these distances. We want to figure out the distances from the angle. We can get the angle now from this formula because we know everything else. So we can say, let's just solve for theta final to start. So we divide Ni sine theta initial over N final equals sine theta final. So theta final is equal to, so I take the arc sine, the inverse sine, whatever you want to call it, of, I'll write it as sine inverse So let's plug in our numbers now. Our initial is 1.0, index of refraction, sine times our initial theta of 72.65 degrees, divided by our final index of refraction of 1.333. Okay, so we take the sine of 72.65, divide by 1.333, take the arc sine or inverse sine of that, and that gives us final theta. Sorry, that should be theta transmitted. I called it theta final, but that's okay. We'll call it theta transmitted. Let's change those. Okay, so our transmitted gets to be a value of 45.73 degrees. Okay, so this angle here is 45.73 degrees. We know that this depth right here from top to bottom is 4. So we know that part of the triangle. So why don't I just kind of write this triangle out here. We know that this is 4.0. We know that this theta is 45.73. Okay? So we can say tan of theta is equal to this opposite over adjacent. So I say tan theta t. I'm just going to call this d. Tan theta t equals d over 4.0. And that's meters. This is meters. Okay, so again we want to find d, so it's d equals 4.0 meters times tan of 45.73 degrees. Okay, that d is 4.103 meters. So that's this distance here. This distance here is d. Okay? So now all we have to do is add d to our 8 meters here. Sorry, L. We'll call that L. So L is going to be equal to 8.0 meters plus d, which is equal to 8.0 meters plus 4.103 meters. Okay, and if we go to three significant digits, our final length is 12.1 meters. And that is your final answer.